It's a great pleasure to speak in this very exciting workshop. Okay. So today I will talk about Brane structures from the perspective of microlocal sheaf theory. So as the title indicates, this talk will center around microlocal sheaf theoretic approach to symplectic topology, especially for Lagrangian intersection theory. So there have been many interesting results connecting microlocal sheaf theory with like the Lagrangian intersection theory. So notably, the Netherland-Zaslow correspondence, so which equates the Foucault category of the cotangent bundle of a manifold X with constructible sheaves on X. Okay. And more recently, there's a work by Dima-Tamarkin, so who has given a definition of a microlocal category on a compact symplectic manifold which is expected to be equivalent to the Foucault category. Okay. So then in this talk, so this work is joined with David Schumann. Okay. So in this talk, so I will present a way to understand Brane structures using sheaf methods. And also I will give a pure sheaf theoretic approach to the Netherland-Zaslow correspondence, which is topological. So purely topological approach to Netherland-Zaslow. So this approach has the benefit that it can be generalized to over any ring spectrum. So it can be generalized to over K, so any ring spectrum. So it will lead to interesting connection with stable homotopy theory. For example, you will see like J homomorphism appear in one of our main theorems. So. Okay. So then the first part of the talk will be introduction, or just a reminder of what is Brane structures in Flower theory, and also give you an introduction to microlocal sheaf theory. Okay. So it's an introduction of Brane structures and microlocal sheaf theory. So Brane structures were introduced in Flower theory in order to have a well-defined Flower cochain complex between two Lagrangian submanifolds of a symplectic manifold. Okay. So to give you the definition of it, if you haven't seen this before, or remind you of this if you're already expert in this, so I will just work in the cotangent bundle of Rn case. Okay. So where things are very simple. So suppose we have a Lagrangian submanifold in T star Rn. Then because we are in this linear case, it admits Gauss map to the Lagrangian Grassmannian of Rn, so denoted by the lag Grassmannian of n, which can be identified with un mod on. Okay. So the map is just take every point in the Lagrangian to the tangent space of the Lagrangian. Okay. So then from this Gauss map, one can associate two cohomology class of L that will be the Brane obstructions. Okay. So there are two cohomology classes L. The Brane obstructions. So the first one is you further compose this Gauss map with the determinant squared map to U1. Okay. This is well defined, so you just choose a representative of your class, so x or n, and then you take like the determinant square of x. Okay. And then because U1 is just S1 and it's BZ, then the composite from L to BZ determines first cohomology class of L in coefficient Z. And this corresponds to one element in this. So this is called the Maslov class. Okay. And then the non-vanishing of this Maslov class is the obstruction to lift this composite map to the universal cover R. Okay. And then the second obstruction is you also do this Gauss map. And then you compose it with like BON. So this is like the classifying map for the tautological bundle on this Lagrangian. And then there's a double cover of this ON, which is denoted by pin plus n. Okay. And then the obstruction class is like the obstruction to the lifting of this map to B pin plus n. So in other words, to give L a pin structure. Okay. And then the obstruction class can be defined by, like you further map this to B squared Z mod 2 by the second Stiefel-Whitney class, then the composition gives exactly the second Stiefel-Whitney class of L. Okay. Then these two classes are the Brane obstructions. And the Brane structure is just a choice of lifting of these two maps. So now this finishes the Brane structures. And then once Brane structures have been chosen for these two Lagrangians, one can define Floer complex. So in this talk, we will only consider like Lagrangian, exact Lagrangian, and in cotangent bundle. So there's no issue about defining this Floer cochain complex. Okay. So then it's well known that this Floer cochain complex is defined by Lagrangian intersections and then counting holomorphic disks. So its definition uses analysis. So however, this Floer cochain complex is of topological nature. So it's invariant under Hamiltonian isotopy by like quasi isomorphisms. Okay. And also one can see the topological nature of it from the Nether-Zeslow theorem. So which equates this Floer cochain complex with the Hom of two constructible sheaves. So these are in M. So that it's really of like topological nature. Okay. Then this the motivation for our work is to find topological understanding like of this Floer cochain complex. I mean, yeah, another way of realizing Nether-Zeslow without using Floer theorem. Okay. So now let's talk about sheaf theory. Sheaves. Okay. So let's first start from constructible sheaves. On manifold M. Okay. So constructible sheaves is a generalization of the usual local systems of K modules to the stratified case. Okay. So what we do is you start with a stratification of my manifold M, okay, by locally closed smooth submanifold of M. And then you can you denote this stratification as a collection of submanifolds. Okay. And then one can define the sheaf category with a constructible condition on S of M. So this is so sheaves whose restriction to each S alpha is locally constant. Okay. So then a direct connection between this stratification theory with symplectic geometry is that you can form the conormal variety of this stratification, which is naturally a conic Lagrangian in the cotangent bundle. Oh, M is the base. Yeah, sorry. Yeah. Yeah, so in this talk, there's no like general symplectic manifolds. Everything is like T star. Okay. So, yeah. So then one can form the conormal variety of this stratification. So this is just the union of all the conormals to each stratum. And this is a closed conic Lagrangian in T star M. Okay. And then for each object F in this sheaf category, one can define a more interesting conic Lagrangian inside T star M, which is always contained in this conormal variety. So this is the so-called singular support of F, or some people call it micro support of F. This is also a closed conic Lagrangian, which is always contained in this conormal variety. So an example, which is the lowest dimension, so you have this R is our base, and then we have T star R. And then, for example, I stratify my R by some points, for example, by 2 points, and then there are complements. Then the conormal variety to this stratification is just the union of the two vertical lines with the zero section. Okay. And then there's some sheaves with this stratification condition. So one is, for example, I can push forward the constant sheaf on this open interval. Okay. So then I can ask what is the singular support of this sheaf. So it turns out it is the union of two half rays and then with an interval. Okay. So it's not the whole of this conormal variety, but part of it. Okay. So in this simple situation, I can explain to you what does this singular support mean. So I still use this sheaf. Okay. And then what does it mean that the singular support contains these two rays and also this one? Okay. So so for example, let's call this A, this is B. Okay, so then our claim is that this positive ray. So this is like positive multiple of dt. So our coordinate is t. It's inside the single support of F. So this means the following. So if I start with an interval on the left-hand side of A, and I start to move the right boundary to the right until it passes through A, and I see whether there's change of my the sections of my F. Okay, so here I see some change. Okay, because I start with 0 section, and then after that I see like one-dimensional section. So there's change of sections. So then I say that okay, this codirection is in the single support of F. So if I move the boundary in the direction of the indicated, I mean this is codirection, but you can imagine that maybe after a metric it's like given a vector, and if you go it in the vector direction, then if you see section change, then you say that half ray is in the single support of F. Okay. And then we can also do a test for the half ray over B. So if we further move this boundary towards B and then until it passes B, so then we don't see any change of section. So it's C and then stays the same. Okay. So then that tells us that this ray is not in the single support of F. Okay. So that's the rough idea how the single support is defined. It's somehow called like non-propagation of F. Okay, very good. So then a central question in microlocal sheaf theory is that so given a conical Lagrangian, so close the conical Lagrangian in T star M. Okay. So find the sheaf category with singular support condition in the conical Lagrangian. Okay. So i.e., so this is the full subcategory of constructible sheaves such that singular support, so F is inside here if and only if a single support of F is contained in this conic Lagrangian. Okay. And usually, one just remembers the infinity end of this conic Lagrangian. Usually one just, so which is a closed Lagrangian in the cosphere bundle of M. Okay. So one only remembers. So, the infinity end, which is like the, you can say like infinity boundary of M, which is canonically identified with the cosphere bundle of M. Okay, so we will denote such a Lagrangian by lambda. Okay. So then one can form the following categories. So first category is from this lambda, you can form like sheaf with single support in the cone over lambda, and then union the whole of the 0 section. Okay. And then this is a category which is interesting. And another interesting category is a localized version of this, so localization of this. So let's denote this category by sheaf lambda M. Okay. And then another category is you do a localization, so you quotient out by local system M, because local system have like single support just on the 0 section. It doesn't touch anything in lambda. Okay. So then one usually view this as invariant of this closed Lagrangian lambda. So maybe I just mention some interesting work along this line to use microlocal sheaf theory to define like interesting invariant of lambda and also apply to mirror symmetry. So first, Nether has developed a theory of arboreal singularities. So with the goal of computing this sheaf lambda m, or maybe the localized one, in general, and he has applied to like homological mirror symmetry. Okay, and there's also like various collaborations of Shende, Truman, and Zeslo, and also with other collaborators. So who studied sheaf R2 with single support in a smooth Lagrangian knot. This is smooth knot inside R3 with the standard context structure. And then they view this as quotient by log, and they view this as invariant of the Lagrangian, and then they have connected this to Lagrangian fittings of the Lagrangian and also to augmentations of Lagrangian contact homology. Okay. That's some interesting results, and there might be other interesting work. Okay, so this finishes the first part of the talk of this introduction. So the second part is the main part of the talk, which will give you a construction of a sheaf of categories. L. So a sheaf, which is a sheaf of categories, so locally constant sheaf. On a smooth exact Lagrangian L, so with fiber mod K. So K can be any like ring spectrum. Okay. And then as the name of this sheaf of category indicates, it will have close relation to Brane structures and Brane obstructions. So, okay. So before talking about this construction, let me just comment one thing about this Nether-Zeslo correspondence. So this is from Fukaya to sheaves, so which relies on Floer theory. So namely, to give this functor, one draw a Lagrangian Brane with some asymptotic conical behavior at infinity. And then to define a sheaf on M, so this is T star M, one just to do the like similar to like family Floer calculation. So you do like Floer cochain complex between every cotangent fiber with your Lagrangian. And then one can show that these glue to be constructible sheaves on M. So really, it relies on Floer theory, and then our aim is to like to give a purely topological realization of this functor. Okay. So let's come to the construction. So first we start from
At some point you should say that for cohomology this was done by Guillermo.
Oh yeah, later, yeah.
Somehow this is the most important.
You mean the compact?
Well, assignment that doesn't use Floer theory, assignment of a sheaf that doesn't use Floer theory.
Oh really? Oh, I didn't know. Okay, okay, thanks. So is it used like the also Sheaf?
No, Guillermo doesn't use any Floer theory, and he maps it to kind of a Sheaf theoretic model in the base.
Oh, okay, probably similar. Okay, okay, I see. So we start from a closed exact Lagrangian P star M. Okay. So let's assume that L is eventually conic. So that means it has like a conical end near the infinity. Okay. And then by exact condition, so this means alpha, the Liouville one form restrict to L is d of a function f, so which is you can just fix one primitive of alpha.
I'm sorry, so L could be compact, for instance?
Oh, L could be compact. Yeah. Yeah.
No,
Oh, no, any closed exact. Yeah, there, we will see like Brane obstructions later. Yeah. Okay. So then if it's non-compact, then we assume it's like eventually conic. And then if it's conical here, so that means so f restrict to this conic end will be like just a constant. Okay. And then, however, in our approach, we want f approaches like negative infinity towards the end. So then one can easily achieve this by doing a kind of Reeb perturbation. So you do like a larger Reeb perturbation when you are closer to 0, but you have to like stop this procedure when you're close to the 0 section. Okay. So then after this perturbation, the Lagrangian looks like this. So something like this. Okay. So after this perturbation, so then f approaches negative infinity near the ends. Okay. So now, so we apply a Lagrangian lifting procedure of this L, which has been used by Demarter-Markin, improving like non-displaceability theorems using Sheaf theory. Okay. Then we do a Lagrangian lifting. So we want to embed L into the one-jet bundle of M, which has a standard contact form. So if you have coordinate QPT, then the standard contact form is, depends on convention. Our choice is negative DT plus PTQ. Okay.
Here, alpha is the one for what?
Oh yeah, here alpha is the Liouville form on cotangent model.
So it's PDQ.
Yeah, it's PDQ. Yeah.
Why do you make this particular group?
Yeah, so I want the front projection of this Lagrangian lifting to like goes to negative infinity end. I mean, I guess eventually one doesn't need this, but for now let's just assume this. Okay. So yeah, so the Lagrangian lifting is the following. So essentially, it's just drawing a graph of f. So you take any point on L to like QP, and then the value of f at QP. Okay. So it's easy to show that this is a Lagrangian because when you restrict this alpha to this embedded to the image, And this is negative df plus pdq. So then it's 0 assumption. And then it has the dimension of a Lagrangian, so it's a Lagrangian. Okay. And then we take this to be a Lagrangian also for the purpose that we view this content manifold as a slice in the cotangent bundle of T star m cross r. So if you denote the coordinate as qp and then t tau, then this is exactly the slice that the tau equals -1. Okay. So then one can, for example, take the cone over this Lagrangian, then it's a conical Lagrangian. Then one can use like a microlocal sheaf theory to study this non-conical Lagrangian. So this was like originated by Dima Tamarkin, this kind of method. Okay. No?
Kashiwara, maybe?
Oh, okay.
It's okay.
Oh, yeah, and Kashiwara. Okay. Okay. So now let's denote the image, I mean the Lagrangian by boldface L. Okay. So then we want to use the Sheaf category with single support in this L, but in a bigger space M cross R, and maybe do the localization quotient by M cross R to obtain, like, for example, information of L. Okay. So eventually our goal is to study this category. And also, furthermore, one can do like push forward to sheaves on M. So we have like pi from M cross R to M. Okay. So one should view like this push forward method, push forward functor will give like something close to Nader-Zessel. So this is some realization of Nader-Zessel. Now let's construct this Brane L. So we do a front projection. So L to M cross R. So namely, just to remember the QT coordinate. Okay. So it's QP here. So in this example, probably this example. So in this example, what you get is the front projection is just this one, with some like wavefront singularities. Okay. And then the wavefront singularities exactly correspond to where your Lagrangian doesn't project submersively to the zero section. Okay. And then for simplicity, let's assume that this projection is like finite to 1. So then one can recover this L exactly from the wavefront projection. So then the L is exactly consists of the negative conormals to these hypersurfaces. And now we are ready to define Brane L, the sheaf of categories. So version 1 of this definition is, of course, use Kashiwara-Shapiro's microlocal sheaf theory. So if you use that, then it relies on a crucial tool, which is called mu-Hom, okay, which seems to be difficult to generalize to the presentable a stable infinity category setting.
So what is the negative economy of
Uh, Yes, over here, because we choose like negative, yeah, so negative. So here, because we embed into like the negative half of the let's see, yeah. So it's like in T star and cross R, but it's like negative half of this cotangent bundle. Okay, so then negative conormal means like your covector C pair with dt is like negative, and here actually it's negative 1. Yeah, so one can use Cauchy-Shapiro, but for the mu harm, it might be hard to generalize to this presentable setting. So instead, we use
What's the name of this tool? Could you write it?
mu harm.
Mu harm. Okay.
Yeah, so then you go to their book, then it's like full of this.
Sure.
Yeah, okay. So so we use a different approach, which which avoids this mu harm, okay? And yeah, essentially use like a stratification theory. So what we do is like you start from. Yeah, because it's like full of like localization categories, and yeah. Yeah, that's right. So let's, for example, we have this wavefront projection. Then we want a locally constant sheaf of categories. So then this is like a functor from the open subset of L. Take op as a category, and then functor to the presentable stable infinity categories over some ring spectrum. Okay, so this is like a pre-sheaf of categories, and then for sheaf of categories, you have to it should satisfy gluing property. Okay, but now here we have like an easier case than this general like a sheaf of categories. Here we require here we want something locally constant, so then it's enough to know its values on like small contractible opens, such that when you restrict to a small open to a smaller one, you naturally get equivalences. Okay. So it's enough to, the values on small contractible opens. And then verify that really under restriction for the small ones, you really get the equivalences. Okay. And then the small contractile opens, you can read out from like this wavefront projection. So this will correspond to like some germ of singularity in this picture, cut off by some small neighborhoods in the total space M cross R. Okay. So for example, here you see a cusp, and here generically you see a smooth hypersurface. And here you see like a double point, but this corresponds to like two disjoint opens in the upstairs L. Okay, so then you should view this like two separate pictures. Okay. So then now we just need to define what is the value of Brane L on such a small open ball. Okay.
Sorry, L, what is L here?
L is the Lagrangian we started with.
Okay.
Yeah, so then L, you can identify, so L and the L boldface are identified.
Okay.
You can also think of this as a sheaf on boldface L. Okay. So then for each like small contractible open L, so you assign the sheaf, the category sheaf with single support in omega, and then with some open neighborhood of the of the front projection, and you quotient by a local system on it. Okay. So then the following.
What's U?
U is like some open that cuts off this this front projection of omega.
Right, so U is some open in the ambient space.
Yeah, U is
Restriction to L is omega.
But ambient space means what? M cross R?
sorry.
What is the U? Is
Yeah, U is living in M cross R. Yes, and then here when you see like a singularity here, it's like preimage. It cuts off this wave front, and then you say like pi inverse U. This is inside like T star M cross R, and then you intersect with L.
At the moment,
Okay, but keep going.
at the moment you're associating some sheaf-like object on L board, right? That's
Yeah, on omega. Yeah, omega is like the cutoff. Yeah, the preimage in L.
So you mean open of L board, not L. Right?
Yeah, but the open omega is in L.
L bold is just an embedding of L into a slightly different command.
Yeah. So L and the L can be identified, or you can say L in boldface L. Maybe that's more natural. Okay.
Yeah. So what's U? What's the dimension of U here?
U, the full dimension. So it's just it's like an open neighborhood. It's like a box. You can
Just write it down.
Right
Oh.
down the
dimension U is dimension M cross R. It's like an open subset in M cross R.
So omega is an open subset of L.
Yes.
and U is an open subset of the front of omega. It's some sort of like open subset of the thickening.
No.
Sorry, the projection.
She said front. She said open subset of M cross R.
Of M cross R. I see. Okay.
But
Yeah.
Okay. So this. Okay. So we are thinking of omega as lying in the
Yeah, like
sphere at infinity of T
Yeah.
star
U. Yeah, that's right. So, yeah, so inside like infinity or maybe it's sphere. It doesn't matter. Yeah, M cross U. Yeah, that's right. Because it's really because it's projected to this inside U, so then it's like living in the.
Okay, but this, okay, I'm just worried this is an open subset of U, but then you say.
Yeah, because here we only consider like half.
No, L
Half.
So I think you mean
So this is independent of the choice of U?
Yeah, this is independent. Yeah. So I mean, you can like one way is like you think like maybe you strict to a small one, then it's just restriction. You can extend bigger, or you can write it as some limit diagram. Yeah.
you wrote down over there, L bold is contained in the hypersurface of particle.
Oh, okay, sure. Yeah. So, yeah, L is. Huh?
Okay, that's fine.
Uh-huh.
That is static what you meant.
That is what?
You could
Huh?
That's fine.
Oh, okay, great. Yeah, so this is well defined as long as your U is like contractible, like a regular neighborhood
So
of
this
that.
depends on the fact that the front projection is locally injective.
Yeah, that's right. It depends on like it's finite to one, finite to one projection. Yeah. So for here, I said yeah. So for double points, you should separate them. So so it's really on like the projection of omega to
Yeah,
downstairs.
but so locally on omega it's injective.
Yeah, that's right.
And locally on L it's injective.
Yeah. Uh-huh.
You still need to know the behavior of the consequences.
Well, I mean, just all you need to know is that, you can make arbitrarily small neighborhoods.
Yeah, it's
on
like
L
topological.
by taking small
Yeah.
neighborhoods on U and intersecting them with L.
Yeah, it's a basis of the topology. Yeah. Yeah. So then,
So then you have to like sheafify it or something.
yeah, but this is already like contractible, small open. So then,
Contractible small. Okay.
But I'm confused by the double point. I mean,
yeah, double points. You should because omega is really this omega is really upstairs in L.
yes.
So at that point, you should like forget about the other branch. So each time you only talk about one branch.
So in static writing, this expression pi inverse u intersect L, that's not necessarily so true.
You mean pi inverse u intersection omega?
Okay. Yeah.
No, I mean, it's just the pre-image in this here intersect.
Double branch.
Oh yeah, it can be like several disjoint. Yeah, but each time you only see one. So that's like the microlocal procedure. Each time you only see one component. Yeah. Okay. So then, yeah. So then the following claim lemma tells us that this defines a locally constant sheaf with fiber mod k. So the first one is for this constructible opens. So this is always equivalent to mod k. But not in a canonical way, so non-canonically.
So now this is not nice, right? Because that lemma you have to, depending on the singularities, you have to prove it for each different time.
Yeah, this is why you need to understand.
Yes.
Yeah, I agree, but there's yeah. So there's some one section in our paper like about like functoriality under like Hamiltonian isotopies of this.
So
Yeah, I agree. Yeah, one has to pay some price because if you just want to use like stratification theory to do this. Yeah. Okay. So this Brane L on omega is always equivalent to mod k, and also whenever you have like a restriction map for two like contractible small opens, then the restriction is always equivalence. Okay, so this is restriction is always equivalence. So this ensures that this Brane L defines a locally constant sheaf of fiber mod k.
So, are you saying that part one of the lemma follows formally from here move quantization of Hamiltonian isotopies?
Oh, this one?
Yes.
Oh, this one doesn't need the Hamiltonian isotopies.
Because you see, you need something for reality. And you straight
Yeah, so for this,
you don't see anything singular?
what do you,
how one is proved.
huh?
We're curious how that part is proved.
How this is proved? So this proved is using like so-called contact transformation.
Ah, there you go.
Yeah.
That's what Alice was asking you.
Oh, I thought it's like a Hamiltonian isotope.
Oh, that's the same. When you lift.
Conical Hamiltonian is fine.
Oh, okay. So then here it's like this is like a long time before their paper. This is also in already in their book, the sheaves on manifold. But yeah, but you can like essentially yeah. So contact transformation is just how you turn this different wavefront projection, or how you turn this embedding of the Legendre ball into like some standard one, which is like a smooth hypersurface. And then this transformation gives you a functor, which is give you like equivalence of localized categories. This hypersurface. So obviously on this hypersurface it's mod k, the localized. So that's how it's proved. But you see that there are like many interesting ways to like do this contact transformation, which gives like a non-canonical equivalence. Okay. Now maybe yeah, I should state the main theorems. Yeah, so maybe just illustrate a little bit how it relates to Brane instructions or Brane structures. So let's just do the example of a cusp. So so on the cusp, this localization category so it's realized by a full subcategory of sheaf with single support here. And then in our convention, this is just the full subcategory consisting of like 0 here and some k module here, okay, inside cusp. And then you create 2 arrows because this is essentially a representation of a quiver. And now you can restrict, you can do restrictions to this upper and lower branches of this cusp. Okay, so then on the upper one you see like 0 n here, and on the lower one you see like n 0 here. Okay. And then in our convention, so then this localized category can be identified with sheaves like this with 0 on the top. So this is something inside here. Okay. And then for this one, this is not in here, so you have to do a localization. So then the answer after doing the localization, you see like 0 and -1 here. So then there's a shift of degree. So then this shift of degrees should be understood to correspond to this Maslov index. Okay, so let me state our theorems. Theorem 1. This is joined with David Schumann. So for here, this L, so for this theorem, so it's about how, so Brane L, so for any locally constant sheaf of categories with fiber mod K, is the sheaf admits a classifying map from L to BPK. Okay, so there's some. This is some group of invertible K modules. So then you should view this as like the automorphism group of mod K, and then Brane L is like a vector bundle on it, vector bundle on L with fiber mod K. So then it admits a classifying map. Okay. So then this is not theorem. Yeah. So then because the sphere spectrum is like the initial object in ring spectrum, so every such map factors through B peak S. Okay. So then it's enough to do the universal case L to B peak S. Okay. So then our theorem identifies this classifying map. The theorem says that Brane L really factors through. So L, you first do a stable Gauss map to U mod O, and then you further apply a so-called delooping of the J homomorphism, and then to B peak S. Okay. So then this stable Gauss map is like you start from T star M, and then you cross like many copies of T star R, and then for L you just cross many copies of 0 sections. And then this J homomorphism is like from Z cross BO to Z cross BGL1S. So it's like from
To Z cross B.
Z cross BO,
It's just
Z cross.
it's hidden behind the.
Oh, okay, I'll write it. Okay, so the J homomorphism. So it's from Z cross BO to Z cross BGL1S. Okay, so the Z component like the virtual dimension. So it's like identity on Z, and then BO to BGL1S is like taking a stable vector bundle to a stable sphere bundle by the Tom construction. Okay, so this is one of our theorem. So this doesn't require L to be embedded. It can be immersed. Okay. And actually, it doesn't need to be like defined for Lagrangian lifting of a Lagrangian. It can be any Lagrangian in the cosphere bundle of like T star M cross R. Okay. Well, actually T star M. Okay. So the second theorem is related to like what I said at the beginning of the goal to identify sheaf with single support in this bold phase L. Okay, the theorem 1 is that so there's a functor called microlocal monodromy from this our goal sheaf sub L mod M cross R. This is to the global section of our sheaf Brane L. Okay. So then one can prove that this is an equivalence. Okay. And then secondly, so if Brane L is trivial, it's a trivial sheaf of category, then after choosing a trivialization of Brane L, then one can get a simpler version of Nader-Zaslow functor. So that is from log L to like sheaf lambda M. So lambda is the infinity of L. So this is a fully faithful functor. So we call it Nader-Zaslow. So it's like fully faithful. Okay. There's a fully faithful functor. So yeah, so Guillemot proved this in the case where L is compact, exact Lagrangian. Okay. So maybe we have 2 minutes left. So the second part of this theorem really follows from the first one. So after you trivialize Brane L, so that means you identify Brane L with so 1 plus 2. So after Brane L has been trivialized, that means you choose the identification of Brane L with the trivial mod K sheaf on L, so which we call it like a curly log on L. So then after this trivialization, then you have a funct. So then you have like a gamma L Brane L. It's exactly can be identified with log L. Okay. And then you use like this inverse functor for this mu monodromy. So this goes to sheaf sub L M cross R. Portion by log M cross R. And then furthermore, you do like a push forward to the base M, so then you get some sheaf with single support in lambda. Okay, and then maybe one last comment about like how it's related to the usual Brane structure. So then the usual Brane structure is a special case with the K is equal to Z. So then when you compose this map, so that's when B peak Z is like BZ cross B squared Z mod 2. So then you compose this map is exactly gives you like L maps to BZ and L map to B squared Z mod 2, exactly the Brane obstructions. Okay, so I should stop here.